We've already seen how you can use the Laplace transform to talk about the transform of the derivative of a function and use that to solve a first order differential equation. Can we do the same thing for higher order differential equations? In other words, can we understand how the Laplace transform applies to the second derivative of a function, or the third, or the fourth? Well, of course, the answer is yes. Here was our formula before for the Laplace transform of the first derivative, f prime of t. You just get s times the Laplace transform of f, and then you subtract the value of f at 0. Well, if we want to find the Laplace transform of f double prime of t, we just apply this earlier formula to f prime. In other words, that's just s times the Laplace transform of f prime minus f prime of 0. That's this exact formula with f prime in place of f. Well, then we have that formula for the Laplace transform of f prime. That just is this formula here, which we put in. We have s times this formula, which is s times the Laplace transform of f minus f of 0. And then we still have to remember we have minus f prime of 0. When we expand that out, that's just s squared times the Laplace transform of f minus s times f of 0 minus f prime of 0. Can we keep doing that? We can do it over and over again. So the Laplace transform of f triple prime is just what we get when we apply this original formula to f double prime, and then we put in what the Laplace transform of f double prime was, and we end up with the Laplace transform of f triple prime of t is s cubed times the Laplace transform of f, and then we have all of these other terms that depend on f of 0, s squared times f of 0 minus s times f prime of 0 minus f double prime of 0. And we can do that over and over and over again, so that in the end, we find that the Laplace transform of the nth derivative of f is exactly s to the nth power times the Laplace transform of f. Then we have all these other terms, s to the n minus first power times f of 0 minus s to the n minus second power f prime of 0, all the way up to minus the n minus first derivative at 0. Now, before we see an example of this, notice that all of these things, this is all information that we would know if we want to solve an nth order linear differential equation with an initial condition that tells us, say at 0, what f of 0 is, f prime of 0, all the way up to the n minus first derivative of f of 0. So if we're given an initial value problem, say for an nth order linear homogeneous differential equation, knowing the initial condition at 0 will tell us exactly all of this stuff, and then we can just transform the nth derivative of f by taking s to the n times the transform of f with all of this other information from the initial value. Let's see how that works. Let's say we want to solve this differential equation. And again, this is one which off to the side you should be able to solve in a matter of a minute or so. Find the full general solution to this differential equation, and then it's a pretty quick thing to be able to solve this differential equation with this initial value, y of 0 equals 1 and y prime of 0 equals 0. So very simple to solve. I wanted to use this example so that you could compare your answer. If you want, you should pause the video now, take out a piece of paper, and actually find the solution to this initial value problem using our techniques from chapter 3. What happens if we apply the Laplace transform to both sides of this equation using this initial condition? Well, the Laplace transform of y double prime is just s squared times the Laplace transform of y minus s times y of 0, which is 1, so you get minus s. Don't forget minus y of 0, but that's just 0. Sorry, minus y prime of 0, which is just 0. Remember, just as before, capital Y is the Laplace transform of little y. So this part here is the Laplace transform of y double prime. The Laplace transform of y little y is just capital Y here. And of course, the Laplace transform of 2e to the t is actually, that would be 2 over s minus 1. The truth is, I'm solving this. Let me change this. I apologize. That 2 should not be there. So my differential equation actually should be y double prime plus y equals e to the t. And now this is the Laplace transform of e to the t. And I want these same initial values. So this is the differential equation I'm going to solve. How would we solve it? Well, When I take Laplace transforms of both sides, I get this. If I just solve for capital Y here, notice you'll get s squared plus 1 times capital Y is equal to 1 over s minus 1 plus s. If I divide by s squared plus 1, y will be 1 over s minus 1 times s squared plus 1 plus s over s squared plus 1. That's what I have here. And then we just want to use a partial fractions decomposition. Now, I won't go through all of that. Let me just say that you can take this and you can write this as 1 plus the s is just s minus 1 over this same common denominator, s minus 1 times s plus 1 squared. The 1's cancel, of course. And you get s over s minus 1 times s plus 1 squared. The partial fractions decomposition of this would be a constant. I'm sorry, that shouldn't be s plus 1 squared. That's s squared plus 1. The partial fractions decomposition is just some constant a over s minus 1. But then because we have an s squared plus 1 here, which is an irreducible quadratic, we can write this as bs plus c over s squared plus 1, and then solve for the constants a, b, and c to make this work. You can find by the cover-up method what a is. That's just what you get when you cover up this first term here and plug in s equals 1 to what's left. That's clearly a equals 1/2. I have that written over here, 1/2 over s minus 1. And then I'll leave it to you guys just to expand and solve for b and c. You'll see that the b is 1/2, which is what we have here, 1 times s and divided by this 2, and the c is minus 1/2. So in the end, you get capital Y is 1 over 2 times s minus 1 plus s minus 1 over 2 times the quantity s squared plus 1. To find our solution, little y, we just take the inverse Laplace transform of this. Remember, the inverse Laplace transform of 1 over s minus 1 is just e to the t, so we have 1/2 times that. That comes from the first term. And then here's some which we might have done in class, but if not, I hope you'll work on these in your homework assignment, and you can verify that the Laplace transform of s over s squared plus 1. I'm sorry, let me change that. The Laplace transform of cosine t will be exactly s over s squared plus 1, so that the inverse Laplace transform of s over s squared plus 1, which is this first part here, the s here, over the s squared plus 1, will be cosine t, and we have that times 1/2. And the Laplace transform of sine t is just 1 over s squared plus 1. So the inverse Laplace transform of minus 1/2 times 1 over s squared plus 1 is the minus 1/2 sine t. And here's what we get for our solution. Now, it's easy to check that for this function. You can probably check this almost immediately. Y double prime, we can compute right away, is 1/2 e to the t. This is y double prime is 1/2 e to the t minus 1/2 cosine t plus 1/2 sine t. So when we look at y double prime plus y of t, the 1/2 cosine t parts cancel, the 1/2 sine t parts cancel, and we end up adding the 1/2 e to the t and the 1/2 e to the t, and we get e to the t. So this is an honest-to-goodness solution to our differential equation. You can check very easily that for this function y of 0 is 1, just this 1/2 plus that 1/2 times 1 plus 0. And if you just differentiate in your head real quickly and plug in 0, you'll see that y prime of 0 really is 0. So this is the unique solution to this initial value problem. Oops, like that. Now, in order to apply these methods of using the Laplace transform and the inverse Laplace transform, you're going to need to know the Laplace transforms of many different functions. And we've only talked about a few in class. On your homework assignment, you'll be doing a lot more computations to learn more Laplace transforms. And I want to bring your attention to the table. So you should all look this up and make sure you're spending time familiarizing yourself with everything. This is the table in section 6.2. I believe it's on page 321. And it contains lots and lots and lots of different Laplace transforms of commonly used functions. So the more you compute, so don't just try to memorize the table. And when I say don't try to memorize it, of course, the more you remember, the better. But instead, look at ones that we haven't computed yet. The more you compute those yourself, the easier it will be for you to both remember those and understand how to work with them. So I highly recommend you familiarize yourself with the table in that manner. And once you become familiar with computing Laplace transforms, and then you'll be able to recognize Laplace transforms and be able to find inverse Laplace transforms, then your work with Laplace transforms will become